Aaron Fike. He's been around for quite some time. His fund has had is in green, and he's a double degree MIT guy. He's had a lot of investments with Khosla, things like that. I was joking with him this morning that, I usually think of the MIT folks are pretty intense and psychotic. So I wonder, with that 2 degrees, what does that mean for him? But I'm looking forward to having further conversations about his fund. I'm going to drag him into Green Lava, which is one of our many communities. We covered a lot of lava bio yesterday with life science. Today's the tech day, and Aaron has agreed to come on board with us and spend the day moderating these panels. So really quick, each of the sessions for the pitches will be a 3-minute pitch. We will be cutting them off, so I apologize. I'm going to be jumping in, or Aaron will be jumping in and cutting them off at the end of 3 minutes. They will get 9 minutes then to do Q&A with our fantastic judges. We're calling them judges, but really they're panelists to provide some constructive and challenging questions and constructive feedback. And so with that, I will turn it over to you, Aaron. And
sure.
At least you're this way on my screen. And I will say thank you.
Absolutely. Thanks, Darren. So yeah, this is day 2. This is the technology track. My name's Aaron Fike. I'm the founder and managing partner of Thin Line Capital. As Darren mentioned, Thin Line Capital is a seed stage fund focused on energy sustainability investments. And so this first session is actually based on energy and materials. So as Darren mentioned, each company will get 3 minutes and we'll have 9 minutes for Q&A. So what I'd like to do to start with, though, is give our judges a chance to introduce themselves before we turn it over to the companies. So I'm not seeing the judges on the screen, but I'm just going to point at Z if you're there. Hey, Z. And I'll let you take it away, and then Alex and Rob can follow.
Hey, Aaron, and hey, everybody. Actually, I think we have at least 3 people on this panel with 2 degrees from MIT, so it's going to be intense, right? So Rob is another one, I think. So he's going to speak in a second. But yeah, so I'm a MIT trained engineer, serial entrepreneur. For the last almost 2 decades, have been investing in and scouting and connecting undiscovered innovators at the frontier. I'm a venture partner with Good Growth Capital, and we're an early stage deep tech fund, primarily focused on the East Coast, but I've joined, have been really focusing on a lot on the West Coast in LA. And we're mostly focused on seed, Series A, first check around 250 to 500K. But we also have some opportunities for super early stage pre-seed, really transformative science kind of things as a sourcing fund as well. We have a different fund for that.
That's great. Rob, do you want to give a quick bio?
Works better if I unmute. Robert Poor here. My thing is cool energy research, and I'm fascinated by all the transformation going on in the energy space and helping companies understand and predict and adapt to whatever those changes are going to be. I also should mention I'm an advisor to Good Growth Capital, and I sit on a couple other boards of mostly Internet of Things for the industrial space. And glad to be here. Thank you for having us.
Excellent. And Alex is not here today, is that correct?
I'm here.
Oh, you are there. Oh my goodness. Alex, take it away.
Hello, Aaron, and hello, everybody. This is Alex Ranopoulos. I'm the Chief R&D Officer of Kairos Ventures. Kairos Ventures is a relatively new VC firm. We have been founded with the explicit purpose of investing in innovations emanating out of scientific labs at universities across the nation. We have, though, our roots here in Southern California. We started with Caltech and expanded our relationships to a number of other universities here in the region, such as USC, UCLA, UCI, and we are very keen in supporting the region and the innovation emanating from such esteemed institutions. In my role as the Chief R&D Officer, I run all the deal sourcing functions and as well as the diligence function here at Kairos. I'm excited to hear about the opportunities that we're going to be listening to in the next few minutes. Thank you for having me.
Excellent. Thanks so much, Alex. So the real stars of today are the companies themselves, and the first company that we have up is BioZen Batteries from UC Santa Barbara. BioZen, you've got 3 minutes, so you can take it away.
I'm Nate Kirchhoffer, co-founder, CEO, and physical electrochemist for BioZen Batteries. I'm here because we're on a mission to make energy storage truly sustainable, and we need to raise $1 million to do that. So right now, we're witnessing a convergence. First, there's a societal movement, and people have bought into using renewable energy in their daily lives. Second, renewable tech is maturing, and it requires safe, long-term storage for its expansion to 50% of global generation by 2050. And third, there's a huge market opportunity with a projected $1 trillion in required total battery storage capacity by 2030. And this must be sustainable. Right now, lithium is the dominant battery material, and it works well in cars and mobile phones because of weight savings. However, there are serious safety and lifetime issues that undermine its effectiveness for large-scale deployment, not to mention that only 5% of lithium batteries get recycled. That sounds dire, but a newer proven technology called a redox flow battery, shown on the left, is projected to be used in about 30% of global stationary energy storage because it has a longer lifetime, meaning 20 years or more and tens of thousands of charge cycles. It can undergo deep discharge, and it has better safety. The dominant redox flow battery electrolyte is vanadium, a toxic transition metal, dissolved in concentrated acid. It's safer than lithium, but it has to be extracted from ore by strip mining, so it contributes about 20 to 40% of the total battery cost, and that is not going to get better. So at BioZen, we replace the vanadium in flow batteries with our secret sauce, a safe, non-toxic, organic electrolyte that performs just as well at lower cost compared to an equivalent vanadium battery. BioZen flow batteries then also disrupt lithium in stationary energy storage applications. On top of cost and sustainability, our electrolyte is recyclable at the end of its life, safe to ship by air, and it can be manufactured anywhere. But our electrolytes are not yet in production, and that's why we're here presenting. We have a detailed plan to optimize energy density, material cost, and battery lifetime to drive our costs down. We need capital to make this happen. The top row of this slide is our business model. We plan to produce and then sell our electrolyte to flow battery companies. Once our tech is proven in real devices, there are a variety of follow-on B2B and B2C opportunities that emerge. We bootstrapped a Delaware C Corp last year, and we've made measurable progress despite the pandemic. We just isolated our first material, and we're submitting a provisional patent. Investing in us is a bet for a cleaner, safer, greener future. And based on our current progress, raising funds in the next 3 months will allow us to start sales in mid-2021 with profitability and break even around 5 years. As a team, we each have over 10 years experience in our fields on top of previous entrepreneurial ventures and several years of developing and selling technical hardware. Bolstering our team with additional business development, sales, and marketing skills is a must. Thanks for tuning in, and I look forward to talking to you.
Perfect. Thank you so much. So we've got 9 minutes for Q&A. Attendees on the Zoom call can also type in questions in the Q&A box, but I'll turn it over to our 3 panelists right now.
Nate, first off, totally agree in the need for the future of batteries, and it's going to be very, very, very important. So I have 2 questions. Are you familiar with the work that Lockheed Martin is doing on non-toxic redox flow batteries? And how do you expect to, what's the differentiator? That's question 1. I'll just stop with that one.
Sure, yeah. I actually just read their patent in the last couple of days. So they're doing a slightly different chemistry. I actually find it quite exciting that they're coming online. It's adding a little bit of momentum to the redox flow battery space.
Sure, of course.
But they're using chelated metal ions, and in our case, we're using organic. So it is differentiated from both an IP standpoint, but also from a chemistry standpoint. So
great. Thank you.
Yep.
And what are your advantages over the Lockheed Martin technology?
I I think theirs is also going to require metal ions. So in the case of like vanadium that I talked about during my presentation, they're going to require some sort of redox active metal as well. It might be more sustainable than vanadium, but in our case, ours is based on carbon. So there aren't going to be mining sites required. We can really manufacture this material anywhere.
I heard there's a lot of carbon around.
Yeah.
So the other thing is, if you've been plotting the cost of, levelized cost of energy or levelized cost of storage, or however you want to compute it, that's coming down geometrically over time.
Indeed.
And I think it's great. I think there's huge opportunities for the people that use that technology, but it does prove to be a bit of a challenge for the people providing that technology. So in the face of eroding margins, what's your plan?
Yeah, great question. So our material actually does reduce the cost of the battery in total. So one thing that I said during the presentation, the vanadium, which is the actual energy storage material inside the battery, it comprises 20 to 40% of the battery cost. And a lot of that comes from the fact that, it's mined and it has to be processed and extracted. Our materials end up being about 4 times cheaper than that. And so we actually do improve the margin on the entire installation of the battery by making this material.
And have you done lifetime tests for the membrane itself? Because it seems to be a weak point in a lot of flow batteries.
We don't specifically test the membrane ourselves, but our materials are compatible with typical membranes like Nafion, which is a really common one. And actually, one nice thing about our materials, unlike some of these current flow battery technologies, which require strong acid, ours is more of a neutral chemistry. And so it's actually not going to degrade the membrane quite as fast. But I acknowledge that is certainly a place that we could innovate in the future, but right now it's not our main focus.
Cool. Thank you.
Hey Nate,
Yep.
what have your customers told you is their largest need? Is it that they need to replace vanadium at all costs, or what? What is it that they need today?
Yeah, so I think the same thing that Rob was alluding to there is, if you look at this cost of production of the battery, vanadium batteries and some of these other batteries are kind of operating on the edge of viability. And so if we can lower the cost of production, we're going to be able to deploy these batteries everywhere. Because I think the main thing that our customers are looking for is being able to deploy alongside renewable energy installations, because renewable energy requires storage. You can't have a solar installation without batteries. You can't have a wind farm without batteries. So our customers really want to be able to profit from enabling renewable energy.
Okay, so you will reduce the cost of the battery by replacing vanadium with your organic electrolyte.
That's right.
What part of the battery is the cost of the electrolyte?
It's something like 20 to 40%. So about a quarter or more of the battery comes from the electrolyte.
Okay, so, and you will be able to take, let's say, that 25 cents to every dollar down to what?
Down to something like 5 to 10 cents.
So I'm just using your most pessimistic part of your range. So we will take it down by 15 cents out of 100, right? We will reduce it by 15 cents. Is that enough? Is that enough? Is that what the customers have said? Reduce it by 15% and we will start buying it in droves?
Well, we don't have a ton of traction yet, so I hope so. But that's an assumption that I want to test with our customers. I mean, we're still pretty early stage right now.
One thing I would mention that probably you and I know really well, and maybe not everyone who's listening knows that well, you're talking specifically about stationary batteries. That is not what you're going to put in your car.
That's right.
And what's more, you probably won't put it in your garage anytime soon. This is probably going to be more like utility scale or community scale storage.
That's right.
So it wouldn't be in an individual home. So your customers are going to, go ahead.
Oh, and I was going to say, that's a great point. Continue, please, though.
So your customers are going to be the utility companies or the local co-ops that need to even out the renewable energy storage. I think that's probably where you're going to find the most customers.
Yeah, absolutely, absolutely. We're not targeting. Oh, go ahead.
Oh, just go ahead. Finish your thought, and then.
Yeah, I was gonna say we're not targeting the residential segment right now, although there is maybe a pathway to get there eventually.
And pardon me if I'm answering Alex's question for you, but if I understand you correctly, because you've got a more docile, less acidic electrolyte, you can expect other components in the system to last longer, especially the membrane, which is a weak part. So there'll probably be other cost savings there as well.
That's right, yeah. And I mean, that's going to become clear as we become operational, but absolutely. Having a non-corrosive chemistry is great for plumbing.
Right.
And that's, these batteries are liquid based instead of solid state. So we actually are flowing the reactant through a cell in the center of the battery. Right. And it, you need that to not break.
I think you did a good job in your presentation of kind of telling the story. And I'm wondering if you could go into a little bit more detail about the sales process, the go-to-market strategy. So, we've talked right now a little bit about who that customer is going to be. What's the sales process going to be like, and what do they need to do in order to change the electrolyte? What is that hurdle going to look like?
Yeah. So one thing that we need is some stronger connections to these companies because they're kind of globally distributed. There's one main one called Uni Energy Technology up in the Pacific Northwest. There's also some redox flow battery companies in China, Japan, Australia, and things like that. And sort of one assumption that we're operating under, which I think is a good one, is that these companies have solved some of the plumbing problem, and to some extent, we're going to be able to quite literally drain their fluid out and put ours in. And so the sales process really is a matter of talking to them and seeing what their pain points are, which I already know one of them is that the cost of the electrolyte is very high. And, if you look at the price of vanadium over time, it's actually fluctuated quite a bit over the last decade. It skyrocketed in 2019 with the trade war. And it's come back down, but it doesn't look to be a whole lot better than it has been in the last 10 years. I don't know if I fully answered your question there, but
part of it too is I think it's really helpful to if you have spoken with customers, it's really important to share that because that's a big it just gives comfort when you're listening to talk, and it makes a big difference if you're guessing what people want, whether you've actually spoken with them. So if you've actually spoken with the customers, please tell us a little bit more.
Yeah, we're still very early. We're still, I would say
okay.
TRL2. So
okay.
Yeah, if you have a connection to somebody that makes financial decisions at one of these companies, I'd be happy to follow up on it. But yeah, we're working on getting into those conversations. Yeah.
So we're gonna have to end it there, Nate. That was fantastic, and yes, I'm a huge fan of storage, so that was interesting to hear what you were talking about. The next company we have up is Fixing CO2. They're from UC San Diego, and there we are. So Fixing CO2, take it away.
So hi, my name is Alma. I'm a founder at Fixing CO2. Where we convert CO2 into clean fuels and chemicals. At Fixing CO2, we strive to disrupt the current fossil fuel-based economy and replace it with carbon-neutral one. We protect the environment by converting CO2 emissions into useful chemicals and fuels. Empowerment of women is demonstrated by our majority female-owned startup. We believe that through research and innovation, we can build strong and sustainable future. Rising carbon dioxide levels in the atmosphere and global temperature increase are serious issues that require collective efforts and extraordinary solutions. Our company is focused on carbon utilization through the electrochemical CO2 reduction. We are building an electrolyzer that converts CO2 to CO using renewable energy such as solar and wind. We can further combine clean CO with clean hydrogen. Get synthesis gas and using Fischer-Tropsch process produce any fuels and chemicals that are currently being produced by the oil and gas industry. We want to recycle CO2 to clean fuels and chemicals using electricity and water and close the carbon cycle. Our technology was developed at UC San Diego. This research was part of my PhD and was funded by JPL NASA as an effort to build a reactor on Mars for the next human mission. We patented this technology through UCSD, and our company has an exclusive license to this tech. Carbon monoxide is used as a feedstock in various industries. The market for CO alone is around $3 billion, whereas the fuels and chemicals market is currently at $100 billion, and it is expected to grow to $400 billion by 2030. We are planning to build a lab-scale prototype by December 2020. For that, we invested our own money, and we recently won British Petroleum Ventures Startup Prize. By September 2021, we are planning to build a printer-sized prototype and perform field tests. And by the year of 2022, we want to build a modular reactor, and for that, we are going to need around $5 million. So this is our team. I'm Alma, I have PhD from UCSD. I previously worked at Stanford and at Caltech. Eldar is a PhD, has PhD from Caltech, and he previously funded a startup in Silicon Valley that was successfully acquired by another bigger company. And Anya, she is our third co-founder. She's a recent PhD graduate from Caltech as well. And we have a great diverse advisory board with the world experts in CO2 reduction. With that, I'd like to thank you for your time. And if you don't want to see a golden haze over the Golden Gate, then join us at Fixing CO2. Thank you.
Alma, that's a very appropriate photo right now. Our panelists, take it away.
Hey, Alma, I've got a quick question for you. You mentioned that your technology is patented. Is the patent composition of matter patent, or is the method patent?
It's the material itself. So it's a catalytic material that is patented.
Very good. And the patent has been issued, or is it in prosecution?
We filed the full PCT patent in April 2020.
Thank you.
Mm-hmm.
So what are the customers saying about your technology? Have you spoken with any yet? And what's the go-to-market strategy?
Yeah, we actually went through the I-Corps, NSF I-Corps, and I'll let Eldar, my second co-founder, answer that question.
Yeah, thank you, Alma. I've spoken to most of the customers. We identified about 3 customer segments in the CO market, which is the market that we're going to attack first. The problem with the carbon neutral fuels market is, first, we need to operate at a large scale, and then there's some techno-economical challenges that will definitely be eased with carbon regulations and things like that, which are unraveling around the world. But we think that attacking the CO market right now is the best bet, where we're already profitable without any carbon regulations. And then there's about 3 segments. The most interesting one is large chemical companies like Dow, Covestro, Mitsubishi, and others who are using CO for production of things like isocyanates and polycarbonates. They need large amounts of CO. They're currently, in North America, they're currently getting it from SMR plants, and they either have pipelines or have gas distribution companies deliver the feedstock. And with this technology, they will be able to produce it on site. We spoke to about over 40 different people in the ecosystem, and a lot in the chemical industry. There's also a smaller segment which we can get to quicker, which are gas distribution companies. They already have a lot of CO2, and they also sell some of the CO. So in fact, there is a product on the market from an adjacent technology of high temperature electrochemistry, where they're already selling to some gas distribution companies in the US. So there's a confirmation of the market needs. Our technology is more energy efficient and doesn't require a waste heat source. So we should, as we scale and as we get to the market and commercialize this, we should get some traction there. Our goal is within a few years, within 5 years, to get to the large chemical industry, but it's, they vary by scale, so it's harder to get to the larger scale.
I missed one thing. What do you use as your feedstock for this?
CO2.
CO2.
But where do you get the CO2 from?
That's a good question. So we think that some of the customer segments, like gas distribution companies, they already have CO2. For the large chemical companies, actually the value proposition is they can repurpose their large CO2 emissions and basically utilize those. It will require some distribution component, but it's very valuable for them. It's probably more important than controlling their on-site CO production. So yeah, we want to recycle the emissions from somewhere.
Can you produce? I'm sorry. Go ahead, Rob.
I was going to simply say, I'm not an expert in the CO2 market, but I know absent any legislation around it, that CO2 itself is a commodity that can be sold. And so you'll actually essentially have to buy it at the market price, it seems.
Right. So the big vision is, of course, when it works at scale, then you can, if you can process large CO2 emissions, then CO2 is valuable, but the distribution component for any gas, the distribution component is the largest cost element. So it's easy to get CO2 for free at, say, an ethanol plant or an oil refinery. But then if you need it, say, 100 miles from there, then it has a price because you have to, package it and distribute it. So the on-site production, that's where it comes to value. Currently, the CO2, the purest CO2 gets from ethanol plants and oil refineries and cement plants. And the gas distribution companies take it from there and then distribute it or redistribute it to their end customers. With CO specifically, it's only made in the Gulf Coast and at the SMR plants. And that's where it's originating and distributed everywhere else from there. And also because it's toxic, not like CO2. For CO, there's a huge transportation cost because there's some regulations on how you can transport it. So we think that even with some price on CO2, and we encountered that price into different models for different customer segments, even with that price, there's still basically CO2 is about $30 a ton, where CO is about at least $400 a ton.
And what is the yield and purity that you achieve with your process?
So our catalyst has very high selectivity. It's around 99 to 100% for CO. And we hope that when we scale it, it will still be at the same level.
99 to 100% purity, right?
Yes. Mm-hmm.
And with that purity, assuming that you can scale, and the costs that you mentioned, Eldar, of I think $30 or $40 per ton of CO2 and $400 for CO, you can produce CO profitably?
Yes, we did the techno-economical analysis. I can probably show some of it here. I don't know if you can see my screen.
We can.
Okay, so we did some techno-economical analysis, and I'm sorry.
Wait, so I think I have the.
Oh yeah, you have the. But I think this one is from a Google Doc. So basically, there is a calculation that ends up in the total CO production cost. The Faradaic efficiency, even if we say at 98%, this still gives us a very good advantage in terms of operational costs. And also the fact that we can produce pure CO basically gets rid of the downstream purification cost with pressure swing adsorption or other technologies, which also saves money. So these are the two main places where our technology gives a advantage in terms of cost. And then, so we think that we will be profitable if we perform at scale on the CO market without any regulations.
Okay, thank you.
I'm intrigued by your distributed model. I think it's really interesting, and I think it's part of the concept behind your business model. And so maybe a little bit more of that emphasis might be helpful. And I'm wondering, you talked about creating you have a prototype that you're planning on having finished in September 2020, and then you're going to have this modular, the next stage is scaling it through making it modular. What is the status of that prototype that you hope to have this month?
Right. So The advantage of this particular technology is that so we have everything working at lab scale, and we're finishing some feasibility studies, mostly to show long-term stability and the slightly larger scale stability of the catalyst. But in order to get to the next stage of a kilowatt scale electrolyzer, we don't actually have to invent our own hardware. There are hydrogen electrolyzers that have been already, there was a decade of innovation in that space where the capex went down. Many companies are working in that space, and so to build a CO2 electrolyzer, what you can do is you can just replace the electrodes on the cathode of a PEM electrolyzer and essentially adjust it so it works at scale. The anode reaction is actually identical. So all we need to do is we need to partner with the hydrogen, with a clean hydrogen producer, and use their electrolyzers and just modify them with our electrodes to build a large-scale system.
Okay, well, I think that's perfect timing. Alma and Eldar, that was really interesting. Thank you for bringing so much data to your talk.
Thank you.
Wonderful. Our next company, and I'm not sure if I'm pronouncing this right, so I'll just